Okay, so now I'm going to explain to you the Jacobian, which is basically the general way to change coordinates, to change an integral from Cartesian coordinates to any other coordinates you might be interested in using. So let me just start by explaining the logic from the point of view of the Cartesian coordinates. And so remember, the idea is that we're trying to work out we're trying to study double integrals, right? Which takes place over some region R on the xy plane. So maybe R is like this. And now dA, you should think of that. Remember, if you thought of f as sort of a surface above the region, then this integral computes the volume between the surface and the xy plane, or the volume of the stuff right exactly above this region R. So this is like notation for sum of many small terms. And so this is height times area. So you should think of this as a very tiny amount of area, which is what you see if you think of subdividing the region into squares, or they don't necessarily need to be squares. You can think of them also as rectangles. But if you start subdividing this region into squares of size dA. Okay? And the idea is that in the Cartesian case, you could think of this little element of area, dA, as either dy dx or dx dy. So I'm going to tell you now a way to think about this formula in the Cartesian case, which will be useful for generalizing it to the polar coordinate case and the more arbitrary case of any coordinate system. Okay, so in the Cartesian case, let's think about what we're doing for a second. Say you have the xy plane, you take a point x comma y here, or more general, it can be anywhere else, and then you can look at lines, a line passing through this point, which is parallel to the y-axis, right? The idea of this being parallel is that being parallel to the y-axis means that x is constant. So let's put x constant here. And likewise, any vertical line that you draw on the xy plane has the property that x is constant. Okay? And by the same logic, you can draw a line that's parallel to the x-axis, right? If this is a horizontal line, then now y is constant, and so you can draw other horizontal lines, right? And all of them have the property that y is constant. So the point that I'm trying to make is that if you, in Cartesian coordinates, you have two coordinates which are x and y, and by setting one of the coordinates equal to a constant, you get curves, right? So the curves that you get by setting x constant are vertical curves. The curves that you get by setting y constant are horizontal curves. Okay? And we saw before that curves have velocity vectors or tangent vectors. And so let's try to find the tangent vectors of these curves. Let's see. So let's take this point. Here we had the point x comma y. Let's try to make this even more concrete. Let's say that this is actually 1 comma 2. The particular details of which point I choose are really not that important. So this is just to illustrate it and make it easier. Right, so if that's the point 1 comma 2, any other point on this line is of the form 1 comma y, right? Because again, this being a vertical line means that the value of x is constant, which is what we had here. So you can think of this as an expression for the position vector of a point on the line, which depends on the parameter y. So now y, which is a coordinate, is being regarded as a parameter for a point on this line. Okay? And by the same logic, if what's the equation of the horizontal line passing through this point? Again, remember this was 1 comma 2. So any point here has to have the form x comma y. Let's call this line r sub b for vertical. And what I was saying in this case is that x can change, but now y has been forced to be equal to 2. So you can think of x comma 2 as the formula for a point on this line. So this is like the equation of the position vector for a point on this line in terms of x. So if you remember when we wrote equations of curves, usually you would write r of t, right? Now the idea being that t time would be specifying a point on the line. In this particular case, since these lines are so simple, it just suffices to specify the points on the line with either y or x. So really like the variable that's playing the role of t is x or y depending on which line you're using. But still the same logic holds that if we take the derivative with respect to time, or in this case the derivative with respect to x or y, then you get a vector that's tangent. So for example, if you take the derivative with respect to x, because that's like the variable in this case of the horizontal line, that's the derivative with respect to x of x comma 2, and that, remember, is the same as differentiating each entry individually. So you get I0, which is a vector I. So you see here the vector I. And by the same logic, if you differentiate with respect to y, which is now the parameter, of the equation for the vertical line, you get the derivative with respect to y of 1 comma y, which is 0 comma 1, which is j. Okay, so you see j here. In other words, in this particular case, the tangent vectors, as you may have already known from like even before doing this, the tangent vectors to the curves are just like the vectors I and j, the velocity vectors. Okay, but what's important to think about this for now is that they were obtained by taking derivatives of the formula for the position vector with respect to the parameter we are using. Okay, and what are we going to do with this? So for each of the curves, for each of the lines, we found the velocity vector. Now remember that this is the key formula. Remember that displacement is velocity times time. Okay, so what I mean by this is that, and this is basically the last thing that I want to say for the Cartesian case. If you had the point 1, 2 here, then you had this blue line, you had the velocity vector which was j, which is again well, zero, 1. Then if you move for some amount of time, the thing that's playing the role of time is y in this case. So usually a small amount of time would be called delta t. Let's think of a small amount of time here as being delta y, because y is sort of in this case like playing the role of time. So if you move for some amount delta y, right, then the displacement would be the velocity times the time. So the net displacement, the displacement here would be velocity times delta y, which is a vector 0, delta y. So that puts you this this point, this endpoint is the initial point plus the displacement. So this is the point 1, 2 plus delta y. Okay, and by the same logic, I should have, sorry, I'll write this on the other side. Otherwise, it will look too crowded for what I'm about to do. So here was, remember this is 1, 2. I was saying that here was a vector j, and here the displacement was j times delta y, which is a vector 0, delta y. So again, the final position is just the initial position plus the displacement, so that's why you end with 1 plus 2, 1, 2 plus delta y. And for the other line, this one that you see here, we know that the velocity vector was I. So you get velocity times displacement in this case the time is like x, so it would be velocity times delta t or velocity times delta x. So the displacement here is velocity, which is I, times delta t, but delta t is like delta x here. So that gives you the vector delta x, 0. And so you get here to the point 1 plus delta x comma 2. And now the idea is that the area here, dA, right? So if you notice this vector, the change in delta x, in x was just delta x, the change in y was delta y. So the area of this small segment is just delta y times delta x. Okay? And basically, well, the point is that here we sort of computed the area by just computing like first the displacements to get like a rectangle, right? A rectangle whose sizes are the changes of these displacement vectors, and then the area is just a multiplication of those displacements, right? So this all looks very silly, but it's I'm putting it this way so that it's clear that we're about to do the same, but for the case of polar coordinates.